In this section, we use the second derivative to find concavity of functions, and we will also be sketching the graphs of the functions. So first of all, what does the word concavity mean, and how do we find whether a function is concave up or down? The concept of concavity is also very closely related to inflection points. So the two come hand in hand, just like increasing and decreasing were related to max and mins. So we say that a function f is concave up if the first derivative is increasing, and we say that a function f is concave down if its derivative is decreasing. So what a graph looks like when it's a concave up graph, it kind of looks like a U shape. And if water were to come down from the sky, you would notice that the water would start accumulating inside the curve. So that's an easy and quick way to visualize whether a curve is concave up or not. So to be concave up, water has to kind of be able to gather inside the curve. Now, you don't have to have a full U shape. Oftentimes we only have half of it. We will still say that this is concave up, or if you have the second half, we would still say concave up. So that's what the first concave up term means. You can also have functions that are concave down, and let me show you what the graph looks like. If you're concave down, it's the opposite. Your function is upside down. Water is not able to gather inside the function. So if water fell from the top of the ceiling or from the sky or whatever, it would kind of just like wash off to the sides. So that's what we call concave down. And again, it doesn't have to have the full N shape. You could have half of that, and you would still call it a concave down function. Now, what is an inflection point? An inflection point is the place where you switch from being concave up to being concave down. So for example, if I was concave up for a while, then I became concave down for a while, the spot where the switch happened is called an inflection point. So that's what we call inflection. Okay, so in reality, how do you find these concavities? Well, in reality, what you do is you test for concavity using this test over here. You check what the second derivative is doing. If the second derivative is positive, we say that the function is concave up. If the second derivative is negative, we say the function is concave down. So let's begin with example number 1 and find concavity. So it's very simple. It's actually very closely related to how we found maximas, minimas, increasing, decreasing. So we begin with the function f of x, first of all. Then we find the first derivative. So in this case, the first derivative is going to be obtained by doing the power rules a few times. So the first one is going to be 3x squared, then 9x, and then negative 9. The derivative of 13 is going to disappear. But we don't stop there, and we keep going. So also, the second derivative is going to be equal to, the derivative again will be obtained by doing the power rule a few times. So the derivative of 3x squared is going to be 6x, the derivative of 9x is going to be 9, and the derivative of negative 9 is going to be 0. So that is the second derivative of the function f of x. We call it f apostrophe because it's the second derivative. So now we're going to ask ourselves the same questions that we did before. What makes the second derivative equal to 0? This happens when 6x plus 9 itself is equal to 0. And that happens when 6x is equal to negative 9, which means x is going to be negative 9 divided by 6. That's another way of saying negative 3 over 2. And the other question we ask is the same question like before. What makes the second derivative undefined? And in this particular problem, the function can not be undefined because the second derivative does not have a denominator, so there's no chance on earth that there will be any forbidden numbers. So we only get one critical value, and it's negative 3/2. So at this point, once you find a critical value, you're just going to draw the line as usual, and you're going to put negative infinity on one side and positive infinity on the other side. And the critical number is negative 3/2. This time though, we got that negative 3/2 from the second derivative, so make sure you write down f double prime on the side, not f prime, because this is the second derivative. And again, pick a number before, pick a number after. So I'm going to pick negative 10, and I'm going to pick 0. Take negative 10, put it into the second derivative, which is 6x plus 9. And you will find that the answer is going to be a negative amount. Take 0 and put it into the derivative, the second derivative, and you'll find that the answer is going to be a positive amount. Now, previously, when we were working with the first derivative, we said negative means the function is going down, positive means the function is going up. This time, though, this is the second derivative. So when the second derivative is negative, that means the function f of x is concave down. And I use the double arrow like that, like an N shape, to refer to concave down. And since the second derivative is positive, that tells me that the function f of x is concave up. So again, I make a double arrow that looks like a U shape to remind me that this is concave up. Okay, so at this point, we are basically finished. So to answer questions 1 and 2, the question part 1 said what's the interval on which it's concave up. So we can say f of x is concave up on the interval from -3/2 all the way to infinity. That's the end of part 1. Now part 2 said what makes, or what interval is the function concave down on. And in this case, the function is concave down on the interval from -infinity to -3/2. And that's pretty much it. Typically speaking, we combine these two questions in one. We don't separate them to part 1 and part 2 because the work is identical for both of them. We don't change a single thing. By the way, -3/2 is going to be called an inflection point. So what is an inflection point? An inflection point is a point on the graph where the concavity switches from being positive to being negative or vice versa. So anytime you have a concavity switching, you end up with an inflection point.